Mahigit 2 milyong
Kaliwat
tonelada
kanan
ng
nating
plastic
napupunta ang
waste
mga
ang
plastic na
nalilikpas
na basura sa bahagi ng ocean sa buong
Pinatapos
ng Maynila at sa barangay
Plastics have become one of the humanity's most powerful inventions, that also shaping the modern lives. And these inventions is we often take for granted, from the packaging that we use to make sure our food is fresh, to the medical field that they use to save many lives. According to United Nations, the world is now produces hundreds of millions of tons of plastic waste annually, which is designated for single use and discarded within minutes. Because plastics take centuries to break down, they accumulate in landfill, waterways, and oceans, threatening wildlife and contaminating ecosystems with microplastics that travel through the food chain.
Better understand the crisis of plastic pollution clogging waterways, we must look beyond the macroscopic view and examine the microscopic chemistry that makes these materials so persistent, especially plastics. Fundamentally, plastics are classified as amorphous solids, specifically polymers that lack a long-range orbit pattern. They are on the side of organic chemistry because they are built upon the element carbon that studies the structure and properties of organic compounds. The secret of plastic durability lies in the atomic structure of carbon itself. Using Nobel gas notation, the electron configuration of carbon is helium 2s2 2p2, derived from its position in group 4A of the periodic table. Unlike the salts in our seas, which forms through ionic bonding, where electrons are completely transferred from metal to non-metal, plastics are formed through covalent bonding. In this process, non-metals atoms like carbon and hydrogen share their valence electron to behave as independent units called molecules. Whether forming single bonds, double bonds, or triple bonds, this sharing of electrons creates a strong connection. As we learn from potential energy diagrams, energy is released when these bonds form, creating a deep energy well. That this implies a significant amount of energy is required to break them. It is this very strength of the covalent bond, rooted in the stable electron of the carbon atom, that makes the plastic in Manila Bay and in the world, or the plastics we use, so resistant to degradation, turning a chemical marvel into an enduring environmental challenge.
One way chemistry can help the Philippines tackle its plastic problems is through biodegradable plastics. These are specially designed polymers that break down naturally over time. Thanks to chemistry, we know how to create plastic bonds like esters or amides that microbes can attack through hydrolysis, turning long polymer chains into harmless molecules like water, carbon dioxide, and biomass. Some biodegradable plastics are even made from natural materials like starch or polylactic acid, which come from plants. By understanding the chemistry behind their structure and reactivity, we can make plastics that serve their purpose but won't linger in our rivers, oceans, and landfills for hundreds of years. Using these plastics could reduce the pressure on our waste management system and prevent harmful microplastics from entering the food chain. Chemistry also allows us to tweak the rate of degradation so plastics last long enough for use but break down efficiently afterward. In the long run, this approach combines science and sustainability to create a cleaner environment for communities across the Philippines.
For solution number 2, we will focus on another way chemistry can help reduce plastic pollution in the Philippines. The solution highlights how chemical water treatment technologies can remove microplastics from Philippine waters. One of the most effective methods is coagulation and flocculation. This process uses chemicals like aluminum sulfate and iron salts, and these chemicals help remove microplastics from water before it is released back into the environment. When alum or iron salts are added to water, they react to form a sticky particles called flux, and these flux have positive charges while most microplastics have negative charges, and because opposite charges attract, the flux attach to the microplastics and neutralize their charge. As more flux stick, the microplastics clump together into bigger and heavier pieces. These clumps either sink to the bottom or are easily filtered out. This means even the smallest plastics, the ones that we can see, can be captured effectively. So, in the Philippines, many wastewater treatment plants cannot remove microplastics completely, but by upgrading these facilities with chemical processes like coagulation and flocculation, we can prevent microplastics from entering Manila Bay, Laguna Lake, and our coastal communities.
And for the third solution, I'll be sharing about algae-based bioplastics for the Philippines. So Philippines has a strong seaweed industry, so we already have access to algae that contain natural polymers. So itong mga polymers na to can be turned into bioplastics. So ito yung mga materials that act like plastics but are renewable and biodegradable. So yung process nito is first, yung algae are harvested and dried. Then, chemists extract compounds such as alginate and carrageenan. So, next is it become the base of the bioplastics by mixing, heating, and adding natural plasticizers. So, the material forms into thin films or packaging. So, since it comes from the natural polymers, it breaks down much faster than normal plastic. So, this solution is nag-benefit siya sa Philippines in three main ways. So, first is we already grow plenty of seaweed, so we have the raw materials. So, second, it can support local farmers and coastal communities by creating new economic opportunities. And third, it offers a cleaner and alternative that helps reduce plastic waste in our environment. So basically, yung algae-based bioplastics won't solve everything, but they show how chemistry can turn a local resource into a sustainable solution for our plastics.